Hello, this movie is for Learning Target 2 in Unit 7, Similar Polygons. Similar figures have the same shape, but not necessarily the same size. You can abbreviate similar with this symbol, which is one little squiggly. You know that we've done congruent with an equals with one squiggle on top. So this just means similar, whereas this means congruent. You can use ratios and proportions to decide if a polygon's similar. Similar polygons are going to be considered similar if two things occur: if corresponding angles are congruent and if corresponding sides are proportional. We will still have all angles, all corresponding angles, congruent. You see listed here. The sides will not be the same length. They will be what we call proportional. So we say that AB is to GH because those are both corresponding. They're between the two right angles. As BC is to HI, so on and so forth. You can identify corresponding sides based on where they are between the markings of the angles. So between one arc and two arcs would be the same corresponding side as between one arc and two arcs on the other polygon. This is called an extended ratio. So you write a similarity statement with corresponding vertices in order. When three or more ratios are equal, we call it an extended proportion. And so when we have polygons of many sides, we'll have corresponding sides having an extended proportion. Now you guys have heard things called scale factors. We have scale factors with similar polygons. The scale factor is the ratio of the corresponding linear measurements of the two similar figures. So these are the corresponding sides give us our scale factor. The ratio of the lengths of the corresponding sides, more simply stated. So always reduce that. Like you reduce slope, you would reduce your corresponding side lengths to see what the ratio is. BC, right here, 20 over its corresponding side, 8, reduces to 5 over 2. So we say that the scale factor of triangle ABC to triangle XYZ is 5 over 2, or 5 to 2. Now that scale factor should hold true for all corresponding sides. Here we have that these two triangles are similar. You can see that they are listed as similar. What are the pairs of corresponding angles? Now you can use the similarity statement. You don't even need the picture because the first letter that's listed, angle M, will be corresponding and congruent to the first letter listed here, angle S. So we have these corresponding angles congruent. N is going to be corresponding with R. Angles are congruent, sides are proportional. So angle N is congruent to angle R. And then we have angle P congruent to angle T. And that would be our last one here. To identify corresponding sides, what's convenient is if I start with MN, I can see it's between the 1 and the 2 arc. So between the 1 and the 2 arc over here would be SR. So I would say MN is 2, and you can also see MN are the first two letters. So the first two letters are SR. We say MN is to SR as, now notice I could do the next two, NP is to RT. And over here you can see that NP is to RT is between these two angles, and it's the same markings on the other one as, and I could do M to P, S to T, and align my corresponding parts. Well, what we see is that corresponding sides are proportional, corresponding angles are congruent. Let's use this statement of similarity between these two polygons, identify the pairs of corresponding angles, and then write the extended ratio for the corresponding sides. Pause the movie, try this on your own, press play when you are finished. All right. You should have D is congruent to H, E congruent to J, F congruent to K, G congruent to L. And then the extended ratio, DE is to HJ, and you can read it, so on and so forth. But you should have 4 of those listed, not 3. Okay, let's look down here. Are the polygons similar? If they are, write a similarity statement and give the scale factor. So when we start to see corresponding angles, I can see that these are both right angles. These are marked congruent. These are marked congruent. And then W and M are marked congruent. So right now, corresponding angles are congruent. That's the first part that we need to make sure is true, holds true. Now the second question is, are corresponding sides proportional? So 6 corresponds to 6. That gives me a scale factor of 1. Well, the scale factor would need to be consistent. This 12 corresponds with 6 here, and if I do 12 over 6, that gives me 2, not 1. So I now don't have a consistent corresponding scale factor. Therefore, these 2 polygons are not similar. So what we would write, you can go through and see that the other 2 sides, the 24 to 16 and the 24 to 14, give you other 2 scale factors. So we say these polygons are not similar since corresponding sides are not proportional. So pause the movie, add that to your notes, press play when you finish. Okay. Here we have 2 triangles. We're seeing if they're similar. So identify if we have corresponding angles congruent. Then identify, do we have corresponding sides proportional? Pause the movie, try this on your own, press play when you are finished. Okay, what we see here, corresponding angles are congruent. Corresponding sides, 8 is to 10, 12 is to 15, and 16 is to 20, all reduced to 4/5, giving us a consistent scale factor of 4/5. Therefore, corresponding sides are proportional. So these 2 things must always hold true in order for us to say that shapes or polygons are similar. Okay. Are the polygons similar? If they are, write a similarity statement and give the scale factor. Pause the movie, try these polygons, see if they're similar. First, see if corresponding angles are congruent, and second, see if corresponding sides are proportional. And then press play when you are finished. Okay, on this first set, 15, which is the largest side here, the longest side, is to 20, the longest side here. Notice I would not do 15 is to 15 because that's the shortest side here. So 15 is to 20 gives me this ratio, scale factor of 3 to 4. Then I would put 10 over 15, which gives me 2/3. So the sides are not proportional. Therefore, these polygons are not similar. On this other one, I've got corresponding angles congruent, and I notice that the corresponding parts, and I've color-coded those, 18 over 9 gives me 2, 18 over 9 gives me 2, 12 over 6 gives me 2. So corresponding sides are proportional, corresponding angles congruent. So that one works. Here we have the 2 polygons are similar. What is the value of x? So to find the value of x, we see that x has a corresponding side of 7.5. So we say x is to 7.5 as, now I can see that I'm looking at y is to 5, but if I say x is to 7.5 as y is to 5, I've introduced another variable, and I've got 2 variables, 1 equation. So I don't want to do that. Instead, what I'm going to do is I'm going to see that 9 and 6 are listed here. So if I have x is to 7.5 as, I need to start with the smaller polygon, 6 is to 9, its corresponding side. We cross multiply here. We get 9x equals 6 times 7.5. That gives me x equals 5. Now I've got that length. To solve for what y is, I see that y corresponds to 5. Now I could say as 5 is to 7.5. However, I found 5. I wasn't given that. So I'm going to go back to what's given just so I'm not building on a mistake if I made a mistake before. As 6 is to 9. And we cross multiply here. 5 times 6. 30 over 9 reduces. 10 thirds. And we can leave it like that. Or 3 1/3. Okay. Your class is making a rectangular poster for a rally. The poster's design is 6 inches by 10 inches wide. So here's our poster, 6 inches high, 10 inches wide. The space allowed for the poster is 4 feet high, 8 feet wide. So 4 feet high, 8 feet wide. What are the dimensions of the largest poster that will fit in the space? Well, we want to make sure that when we're enlarging the poster that we're not going to augment it in any way. So we want to preserve its ratio. So that means that we need to figure out 6 can be increased how many times to fit into a 4-foot space. And then we also need to see 10 inches could increase how many times to fit into this space. So we first need to get these guys into the common units. 8 feet is 96 inches. 4 feet is 48 inches. And so we see that 96 inches divided by 10 inches gives us 9.6. And we see that 48 inches divided by 6 inches gives me 8. So what I'm noticing here is that the height could increase by 8 times to fit into the space, and the width could increase 9.6 times. So I need to do the smaller amount because if I do the larger one, the height will not fit. It'll extend past the space allotted for it. So I can't use the 9.6. So what I need to do here is take this times 8 and this times 8. And I see that I get the 48 inches. And then I do 10 times 8 gives me 80 inches. So I get 48 inches by 80 inches. That's the amount of space it will fill. Pause the movie, try this one on your own. Press play when you are finished. Okay, let's look at this one. 6 inches by 10 inches was our original. We're fitting it in a space that's 3 feet by 4 feet. Converting to inches, we get 36 inches, 48 inches. We see that the width could increase 4.8 times. And the height could increase 6 times. Well, I can't do 6 because that would extend too much for the width. So I use the 4.8 and I take both dimensions and multiply by 4.8. I get 28.8 inches by 48 inches. If you would like more practice, there is this. In a scale drawing, all lengths are proportional to their corresponding actual side lengths. The scale is the ratio that compares each length in the scale drawing to the actual length. The lengths used in a scale can be in different units. For example, in a scale, it might be written 1 centimeter to 50 something, 15 miles, kilometers, 1 inch per 100 miles. So you can have different units when you're looking at a scale. You can use proportions to find the actual dimensions represented in a scale drawing. This happens multiple times in a map. One of the most frequent questions I get is, how do you write it? Is it always the scale over the actual, or how is it written? And I always think DA, drawing to actual, DA. So you take the drawing length, and that's usually inches, centimeters, and that goes over the actual length in real life, number of miles, number of meters. And that's how you write a scale factor. Let's look at the Golden Gate Bridge in San Francisco. The distance between the two towers is the main span. Let's say that this main span on the map is 6.4 centimeters. We have a scale drawing of 1 centimeter per 200 meters. So I'm going to use that. 1 centimeter per 200 meters should be equal to 6.4 centimeters over x. And I can cross multiply and solve for x. It does not matter that you're in different units as long as you are setting it up consistently. Centimeters per meter, centimeters per meter. If I were given the actual length, I would have my variable in the top, and I would put my actual length down here because that would be in meters. We're going to cross multiply this. 6.4 times 200, and that gives me 1280 meters. 1,280 meters would be the actual length in real life. You want to make a scale drawing of a New York City's Empire State Building. Here's your scale. And if the building is 1250 feet tall, how tall should you make the building in the scale drawing? Pause the movie, set this up, press play when you finish. Okay. Drawing to actual, 1 inch per 250 feet. So I've got inches over feet, cross multiply, you should get 5 inches. And that's all we have for this movie on Learning Target 2. Please check with me if you have any questions. Thank you.